Welcome all. Thank you for joining today's session. This is the sixth and the last session of Grapes to Wine Cool Climate webinars. My name is Neslihan Ivit. I am the Winemaking and Innovation Specialist with Perennia, and our co-host is Francisco Diaz. He is the Viticulture Specialist with Perennia. Today's topic is flavor chemistry and canned wines. And before jumping into our speaker, I would like to give some Zoom housekeeping items. You will have your audio and video turned off during the webinar, but we do encourage you to make questions. And for that, please use the Q&A feature at the bottom of your screen. And Francisco will collect your questions and ask to our speaker at the end of the session. And I also would like to remind you that the session is being recorded and you will be able to watch it on demand. A brief introduction about Perennia. Our vision at Perennia is rendering Nova Scotia a recognized world leader in producing innovative, environmentally responsible, and high quality food. And our mission is supporting growth, transformation, and economic development in Nova Scotia's agriculture, seafood, and food and beverage sectors. We have a wide range of service areas. We cover agriculture, quality and food safety, product development, lab services, and also fisheries. And our wine-related services start from the vineyard with size assessments, and we have viticulture services, a plant health lab, various winemaking services, a mobile bottling and filtration line, and finally, business development services. With that, we accomplish a full circle of services. And today's topics looks at the canned wines. And if we give a general look about wine packaging, we see that there is an ongoing trend of innovation in the wine packaging. And there are different reasons behind these trends. For example, the increased awareness in being sustainable changed some of the material that are used in the wine packaging and made ways to find material that have lower carbon footprints than the glass. Or difference in the lifestyle of the people bring some size differences like single servings or even bigger sizes. And again, being sustainable and environmental friendly and be the interest of easing the shipments and also saving the weight on the wines, and as well as avoiding waste, which is very important, bring these different options of material, size, and shape. And looking at all different innovations, we see that canned wines have been gaining a lot of popularity in the last years. And today we can see different wine types and categories in cans. We can see white wines, red wines, rosé wines, and also orange wine in cans in still or sparkling form. And even though in the beginning we had more entry-level canned wines, now we see that some of the premium wines are also entering into the can. But when we look in the winemaking side of the things, the questions comes as how does canning affect the wine quality? And currently there are new studies being conducted to discover more the effect of canning in terms of quality or shelf life. And today we will look at one aspect of this topic, and it's great to have the expertise of Rachel Ellison for this. Rachel Ellison has a Bachelor of Science in Engineering Chemistry from Queen's University, and currently she's a Ph.D. candidate at Cornell University, working with Dr. Gavin Sachs in wine flavor chemistry. She received graduate and postgraduate scholarships from Natural Sciences and Engineering Research Council of Canada, and she also received a President Award Scholarship in Enology from American Society of Enology and Viticulture in 2020. Her research focus is the evolution of reductive of aromas related to cup refining and canned wines. And with that, I will leave the screen to Rachel. Thank you very much.
Thank you for that introduction. I'm happy to be here today to talk a bit about flavor chemistry in canned wine and cans in comparison to some other types of alternative packaging, and where we think this kind of packaging is going, and some of the research that we're currently doing in the lab group at Cornell. So as Neslihan mentioned, my name is Rachel Allison. I'm a PhD candidate at Cornell. I'm in the Department of Food Science, which is in the College of Agriculture and Life Science. And my research area is wine flavor chemistry. So I'm going to give some background and then dive into a bit of the research that we're actively doing. So there has been significant growth among alternative packaging types for wines over the last few years, particularly when compared to conventional glass bottling. And among these alternative, canned wines are growing the fastest. Part of this is because the initial share was really just so small to begin with. But a recent report has also shown that global canned wine market is expected to go to over $150 million by 2027. And there are a lot of reasons why cans are a very attractive type of packaging to use. So first, and possibly foremost, aluminum is a really good gas and light barrier. And as we know, wine is sensitive to both of these. The type of seal that you can make with an aluminum can, it's a double seam, and it's effectively a hermetic barrier. Secondly, cans are very recyclable. So aluminum is considered indefinitely recyclable because it retains its properties through multiple renewals. And further, consumers actually do recycle aluminum cans at a very high rate, higher than any other type of packaging, really. And because of that, a lot of aluminum cans have a high percentage of recycled material in them. So the use of aluminum in other types of beverages, obviously besides wine, and in other types of food products, also means that the recycling streams for processing aluminum are widely established and well run. And so by contrast, other types of alternative packaging, some things like multi-layer packages, Tetra Paks, tend to be difficult to recycle because it's usually different types of materials that are bonded together. They're difficult to separate and they're difficult to recycle. And plastics tend to degrade and lose their properties over time through multiple recycling. So they're less favorable in that sense. Paper and plastic recycling streams are also getting more and more expensive these days compared to aluminum. A third advantage is that cans are very lightweight, and therefore they're less expensive to ship compared to conventional glass. And for an equivalent amount of wine, a can is about 30 times lighter than conventional glass. And then finally, canned beverages. The canned beverage markets are growing, and they appeal to new consumer segments. You know, they're convenient, they're light to carry, they're available in smaller portions, and they're appropriate to a lot of venues where glass might be prohibited, things like beaches, concerts, and festivals. But what is interesting is that what we see with canned wines is often the creation of new market opportunities rather than the cannibalization of existing markets. So there are plenty of practical advantages, but we have to consider also how it affects the product quality. And we can do this through the lens of flavor chemistry. So when we talk about flavor chemistry and quality, we are generally interested in three processes. The first is flavor degradation. And we're asking, is the material an effective gas barrier? The second is scalping. Does the material bind or absorb any of the desirable flavor compounds? And then the third is tainting. Does the packaging release or facilitate chemical reactions which produce off aromas? So we're going to talk about the first two processes in cans and in relation to other types of packaging, but we're really going to focus on that third process, tainting, and look at both the results of reaction facilitation and reaction with the packaging itself. So let's start by first considering flavor degradation, which in wine is results from SO2 loss due to oxygen ingress or oxygen getting into the packaging. So let's say we bottle generally around 30 milligrams per liter of free SO2 to help keep wine tasting fresh and bind up oxidation products. SO2 is lost over time as it binds to oxidized compounds that are formed as oxygen gets into the packaging. And so on a molar basis, we lose SO2 at a rate of 1 mole of oxygen ingress to 2 moles of SO2 loss. And in terms of SO2 loss and oxygen ingress, what do we see when we look at cans and other types of packaging? What we see is that over time, the rate of oxygen ingress is much slower in cans than in other types of packaging. So cans have excellent oxygen barrier properties, as I mentioned previously, largely because metal is impermeable and the sealing process produces a double seam. So if you can limit total package oxygen during canning, the total oxygen pickup, which can be more challenging with, say, still wines compared to carbonated products, you can still, with most good canning operations, limit the TPO to levels comparable to other types of packaging. So any amount of pickup can pretty much be neutral across packaging. But because the rate of ingress is so much slower in cans, what we see is we estimate from the available literature that even with the worst practices in terms of total package oxygen pickup during packaging, canned wines are going to have a much longer shelf life in terms of SO2 loss compared to other types of packaging. So we see in this table, for example, that canned wines have a very slow rate of oxygen ingress and would have theoretically an extremely long shelf life. The next longest shelf life would be something like a screw cap, which we know to have very good oxygen barrier properties, followed by natural cork, a synthetic cork, and then with very short shelf lives, kind of at the low end of that scale, would be things like a bag-in-box, which are very susceptible to oxygen ingress. So it should be noted also that this data refers purely to an SO2 loss perspective. So cans are theoretically able to sustain their SO2 levels even twice as long as screw caps, but you should still not keep any wine in a can for 20 plus years because you would definitely encounter other issues of corrosion and degradation that are unrelated to the loss of SO2. But it is important to note that when we talk about flavor degradation, cans are a very favorable type of packaging. So we're going to talk about scalping. And before we do that, we need to look at a bit at the anatomy of the can to understand what materials we're actually dealing with. So you can see from the cross-section illustration of a can that the material directly in contact with the wine is called the liner. So it's the inside of a wine can or any beverage can is spray or laminate coated with a very thin polymer lining. And so a wine can is effectively just a plastic bag of wine with a metal exterior to give it a rigid structure. So it's really the plastic that holds the beverage. And so shown here, you can see a can where I've etched off a section of the aluminum metal to expose the polymer lining beneath. So I use caustic chemicals to dissolve off the aluminum, and now you can see the plastic, and it's just a thin layer of clear plastic, and you can see the wine right through it. So these lines are typically epoxy-based resins, historically BPA epoxies, but the trend is to move away from BPA-based epoxies. But the takeaway here is that the wine is in contact with the plastic, not the metal. So this is important because food plastics are known to scalp volatile aromas. And that's a particular concern for us when we deal with wine, since scalping does not occur uniformly across compounds. So it can both decrease the intensity of aromas by absorbing compounds, but also alter the balance of the aroma profile. It doesn't scalp everything evenly. And as we know in wine, balance is very important. So the amount of scalping will depend on the thickness of the plastic used. And so across packaging types, PET bottles are generally the thickest, around 300 microns. So our concern for scalping is pretty significant for that type of packaging. Things like multi-layer packs kind of have a range of plastic use, but in the range of 10 to 100 microns. Polymer liners in cans, and there are polymer liners, by comparison are very thin, so usually in the 1 to 10 micron range. So while scalping is technically a concern, it's really negligible in comparison to other types of alternative packaging. So it's more plastic than just using glass, but it's much less plastic than any other type of alternative. So relative to other types of alternative, this is kind of the best way to go if we're concerned about scalping. So that brings us finally to tainting. And we do have some concerns when it comes to canned wines. So some canned wines are reported to develop hydrogen sulfide during storage. And this has the aroma of rotten eggs and is widely regarded as a fault. and contributes to consumer rejection. So this issue we know affects some canned wines, but definitely not all products. So we need to look more closely at this phenomenon to understand what's going on. And before we do that, we just want to quickly review the issue that hydrogen sulfide poses to us in terms of wine quality. So among premium wines, about 25% of faults identified are classified as reduced, and that is characterized by the presence of hydrogen sulfide and related sulfur-like off aromas. So in such wines, hydrogen sulfide is usually present above its threshold concentration, and so it's often used as a marker for wines that are reduced. So hydrogen sulfide itself is highly volatile, but it can combine with other components of the wine matrix and lead to the formation of other malodorous volatile sulfur compounds with aromas ranging from rotten cabbage and oniony, garlicky smells to burnt rubber and struck match. So there are several options we have for remediating excess hydrogen sulfide prior to packaging, but there isn't really anything we can do about it once the wine has already been either bottled or canned. So I will be elaborating on two sources of hydrogen sulfide that we believe are important to consider in canned wines. So the first is related to copper fining, and the second is related more directly to reactions between the SO2 in our products and the aluminum metal of the can itself. So let's start by looking at hydrogen sulfide production that's related to copper fining. So to illustrate the implications of copper fining, let's consider a white wine that has developed some excess hydrogen sulfide. We can add copper sulfate to bind up this hydrogen sulfide and form copper sulfhydryl complexes, or copper sulfides generally. But whereas these complexes were previously thought to form a precipitate that could then be removed, recent work by Clark's group has shown that instead these complexes form nanoclusters that remain dispersed in the wine. And that means that they can later serve as precursors to hydrogen sulfide. So in fact, at least 79% of the copper added during fining is found to remain in the wine after racking and filtration. So all of these copper sulfides that we think we're removing are not actually being removed, and they stay in the wine. And that means this wine, having been treated, it smells fine, it smells great. We put it into bottle, but then after storage, and storage is a very reductive environment, hydrogen sulfide can reappear. Again, it doesn't happen in all products, but it definitely happens in some products. And we want to know if that's our product. So in summary, copper fining makes these metastable copper sulfhydryl complexes that remain in the wine. And those products undergo storage in a reductive environment or a low oxygen environment. And then we sometimes see hydrogen sulfide reappearing from those compounds being reduced. And this happens in wines in bottles. So by analogy, what does that mean for us in cans? Well, as we discussed, one of the advantages of cans is that it has excellent oxygen barrier properties. But in this case, that's kind of a double-edged sword because the excellent oxygen barrier protects the wine, but a low oxygen environment also creates the reductive conditions that favor hydrogen sulfide. So canned wines have very low oxygen ingress and thus a very reductive environment. And a reductive environment can result in hydrogen sulfide. So what we have is, in light of this reductive environment, it stands to reason that copper sulfhydryl complexes in canned products are even more likely to result in hydrogen sulfide reappearance during storage. So if you have these precursors and they aren't stable, putting them in a can environment means that they are in an environment where they're more likely for the complex to break apart and release hydrogen sulfide. So what we see here is that the packaging creates an environment that facilitates release of hydrogen sulfide from precursor complexes. Okay, so we've talked about copper fining, and we're going to move on to reactions of SO2. And this is kind of the more acute issue that we're dealing with that is specific to canned wines. So the other issue affects bottles as well. This is specific to what we're seeing with cans. So let's just jump back to the anatomy of the can, if you will, and look at the cross section. So we know that there's a liner, and then we also know that we can see that there's illustrated here some other barriers between the aluminum. So we have alumina as well. And so the takeaway, as I said, was that the wine isn't in direct contact with aluminum. There are barriers that prevent or should prevent their interaction. So knowing that there's barriers between the wine and the aluminum, where is this hydrogen sulfide coming from? So what we do know is that hydrogen sulfide has been shown in different works to be produced when uncoated aluminum alloy is exposed to either wine or model SO2 solutions. You get hydrogen sulfide. None of this work was done in canned wine specifically. Well, our work is, but this, previous work was not done in canned wines. But the canned wine patent literature, which is where we find a lot of interesting observations, also suggests that there's a relationship between SO2, aluminum, and hydrogen sulfide formation. So that's the direction we start looking at. So how much do we see this problem? Well, as I mentioned, the literature is very limited, but from our surveys of different canned wine producers, what we hear is that hydrogen sulfide is rarely, if ever, reported in red wines. However, in some canned white and rosé wines, hydrogen sulfide is sometimes reported, and we estimate that 10 to 20% of cans on the market experience this issue. So why are some of these whites and rosés at risk of developing hydrogen sulfide, whereas the canned reds seem fine? Well, we think that it comes down to the forms of SO2 that you have in different types of wine. So the total SO2 is going to be the sum of your free SO2 and your bound SO2. In whites and rosé wines, total SO2 is mostly just free SO2. And so free SO2 means that it's free to interact with the packaging. If the opportunity arises, it's chemically active. However, in red wines, most of what we actually measure as free SO2 isn't really free, it's bound SO2, and it's weakly bound to anthocyanins, producing these weakly bound adducts. And that means that it's not really chemically available to interact with anything else. So I mentioned that the total SO2 is the free plus the bound. And we're interested in this free fraction, which further breaks down into molecular and bisulfite. And I'm sure many of you are familiar with this, but the free SO2 is the free SO2 is made up of these two fractions, and the molecular SO2 is the minor fraction, which has antimicrobial activity, and bisulfite is the major fraction, which has antioxidant activity. And so while we can arguably achieve microbial stability by other means than SO2 in wine, the level of antioxidant activity that we need for most wines requires the use of bisulfite. It's very difficult to avoid dealing with SO2 entirely and maintain any type of stylistic integrity. So we can't avoid the issue we can't avoid SO2 being an issue by just not using SO2, because it would be very hard for us to be making what people recognize as wine at that point. So the reason that it can be hard to perceive the difference between reds and whites and rosés in terms of the SO2, the free SO2, is because of the way that we measure SO2 in reds. So when we do this by conventional methods, we actually end up disrupting all of those weakly bound adducts, releasing them as free SO2. So we inadvertently overestimate free SO2 in red wines, which is why the differences between reds and whites and rosés is not always apparent. But if you compare the SO2 by measuring molecular SO2 directly in reds, whites, and rosés by a more or a less disruptive headspace method using gas detection tubes and compare it to what you would get calculating from AO, you find that AO actually overestimates molecular by a lot. So AO and conventional methods tend to be too disruptive to accurately measure free and thus molecular or bisulfite. So to summarize our understanding and approach this system, SO2 in whites and rosés is free and can potentially interact with the aluminum. SO2 in reds is bound to anthocyanins, and so we don't typically observe much hydrogen sulfide. So SO2 seems to be driving this production of hydrogen sulfide, but how does it actually come in contact with the can, given that we know there's protective barriers between the wine and the aluminum? So we hypothesize that the dominant pathway is that molecular SO2, because it's a neutral dissolved gaseous species, can diffuse through the liner. Because neutral species can diffuse through non-polar plastics, and the liner is just a polymer. So this makes it important for us to have an accurate sense of how much molecular SO2 we actually are dealing with. And then considering the thinness of this polymer liner, we think that it can also have defects or imperfections that could allow molecular SO2 or even bisulfite, if we're dealing with the case of like an actual pore, to pass through and interact with the aluminum. So in some of our preliminary results in our work, we've actually seen some anomalously high hydrogen sulfide production in localized sections of coating. And we think that could be attributed to liner inconsistencies or defects as a route of interaction. So there is one other barrier between the wine and the can, and which you've seen illustrated in the various cross sections, and that is the non-reactive aluminum oxide layer, or alumina, which forms on an aluminum exposed to air, just naturally forms. So this illustration is not to scale, but it's just a very, very thin layer, like on the scale of a few nanometers. So this does provide some additional protection between the reactive aluminum and the wine, but it is susceptible to degradation when exposed to acidic solutions. This is not something that's been studied specifically in wine, but in a lot of other beverage systems. And given the pH range of wines, and particularly for us in our cooler climates, the pH range of our wines, we're dealing with systems that are acidic enough that the alumina, which is non-reactive, is susceptible to degradation. So this kind of gets towards our actual research. And so in some of our preliminary trials, we've taken wines and then modified them to have different combinations of low and high pH, low and high free SO2, molecular SO2. And what we see so far is that molecular SO2 seems to be a better predictor of hydrogen sulfide than either free or bisulfite. What we know is that lower pH wines have a higher proportion of molecular SO2. That's just how the equilibrium works. So it seems at this point reasonable to be particularly cautious when we're canning very low pH wines, which is often a concern for us in our cool climate regions, and to make sure that we're mindful of our molecular SO2 levels. So as the relative fraction of molecular and bisulfite depends on factors in addition to pH, there is more than one stylistic chemical property that we're actually trying to balance in a wine that's destined for can. So not just pH, but also ethanol and ionic strength will influence the equilibrium proportions of molecular SO2 and bisulfite. So a final note that is kind of interesting to us is that typically red wines tend to have higher pH than whites and rosés. And it kind of further supports why we don't see this issue as much in reds, or nearly as much in reds as we do in the lower pH whites and rosés. So I'm going to transition a bit into our ongoing research goal. So our aim is to improve the metrics for deciding which cans are appropriate for which wines in order to minimize the risk of hydrogen sulfide. So first, we're developing an accelerated aging model to assess different kinds of can liners. And then second, we are looking at other potentially corrosive components in wine to see if there are any synergistic effects in producing hydrogen sulfide. So I'm going to elaborate a bit more on the first objective and describe our accelerated aging method. So in our lab, we've developed these rapid and expensive methods for measuring hydrogen sulfide in wine using commercially available gas detection tubes. So running one sample takes less than 15 minutes, and the cost of consumables is at most $10 per run, often less, depending on the kinds of concentrations you're working with. So this glassware is mainly adapted from a standard AO unit. So well, we did this because in the lab, I just didn't want to have to buy more glassware, but the method has been adapted for use with either sparging with an inert gas, as shown on the left, or with vacuum aspiration, as shown on the right. So it's fairly adaptable to a lot of common lab setups. And the method has a limit of detection well below the odor threshold for hydrogen sulfide in wine. So it's pretty adaptable to and applicable to winery type measurements. And we use this for all of our hydrogen sulfide analyses. So briefly, hydrogen sulfide is forced through a gas detection tube. So forced out of the sample and through a gas detection tube where a colorimetric reaction occurs. And this can be used to quantify hydrogen sulfide. So the colorimetric change is compared to a calibration curve, which in our experience aligns very well with the theoretical capacity of these gas detection tubes and has very high reproducibility. So for the validation of this accelerated aging method, we are working with 3 types of commercial liners, an epoxy acrylate, and an acrylic. And then we have selected 10 commercial wines representing different styles and chemistry. And for accelerated aging, what we do is we take a small cutout of aluminum, which is just called like a coupon, and it has one of these 3 commercial liners. We then seal off the exposed cut edges and incubate the coupon in a small vial of each of these 10 wines at a high temperature for a couple of days. that's the accelerated version. And then we compare it to a regular storage situation where we take commercial cans with these same 3 liners and we can out all 10 wines the same way. And we're keeping those under just normal storage conditions and testing them every few weeks over a period of about 9 months. And so in determining the relationship between these 2 scenarios, we will have a way to quickly assess whether a particular wine is appropriate for a can with a particular liner. So this is just a sampling of some of the accelerated aging results that we've been getting in our experiments. And I just wanted to show you this to see the kinds of trends we're seeing in these results. So what we want to show you here is that in general, we see less hydrogen sulfide coming from epoxy, more hydrogen sulfide coming from acrylic, epoxy acrylate kind of somewhere in the middle. And these are some of the results from some of our whites, a selection of our white wines. And we saw similar things in our rosé wines where we do see quite a bit of hydrogen sulfide produced. However, in reds, we see very little. The scale of this red wine is much lower. And so a summary of all of that, using this gas detection method to measure all of these samples, we really do see these trends pan out across all the wines that we were looking at. So the whites and rosés produce more hydrogen sulfide than the reds. The epoxy performs best. So the classic BPA epoxy performs best and the acrylic performs worse. And then epoxy acrylate is kind of an intermediate chemistry. So we kind of expect that to be somewhere in the middle. So the samples that produce the most hydrogen sulfide, the ones that seem to us most risky right now to put in cans, would be our white wines in these acrylic lined cans. And the samples that produce the least hydrogen sulfide, so the most stable in that regards, are red wines in the classic epoxy lined cans. But what is interesting to us is that in any combination of factors, the range of hydrogen sulfide concentration can be quite broad. And even in this early data, we can see that clearly that both the choice of wine and the choice of liner matter. There is no liner that is absolutely good and no wine that is absolutely good. So this is like an interesting place for us in terms of the long-term storage study that we're comparing it to. So to just touch briefly on the second objective of our project, we're looking also at other components in wine which may exacerbate or inhibit corrosion to see if there are any synergistic effects in hydrogen sulfide production. So chloride and copper have been cited particularly as corrosive factors in other aqueous metal systems at concentrations that are similar to what we find in wine. So those are of particular interest to us. We have also observed that in some of our preliminary trials that polyphenols can have a passivating effect on aluminum, rendering it almost like inactive. And so we detect no hydrogen sulfide in situations where we really should. And so we're also throwing that into the mix as it's an important component in wines. And then finally, I've seen in some of my previous work, and it's been reported from other groups, that the presence of free thiols in wine can influence the activity of copper. So whether it is going to impact aluminum corrosion or whether it's going to, after hydrogen sulfide formation, bind up hydrogen sulfide. So the activity of copper can also be influenced by the presence of free thiols. So that's also another factor that we're including in these mixed model systems. So we're considering model wines with different levels of these compounds or these components, copper, chloride, polyphenols, and free thiols, as well as controlling SO2, pH, ethanol. And so we're applying accelerated aging methods to these analyses as well. And we're trying to narrow down this multifactorial approach to the dominant factors so that we can provide faster information for producers to make decisions on whether their wine is appropriate for cans. So just a few concluding thoughts before we wrap up here. In terms of the flavor chemistry-driven wine quality markers, some wines are truly just chemically better suited for cans than others, given the current liners that we have available. So generally speaking, red wines seem to be lower risk in can, although at least in a model solution or in the lab, we can definitely modify a red wine so that it produces hydrogen sulfide. So lower risk doesn't mean zero risk, but lower molecular SO2 wines also generally seem to be lower risk. And to make a call as to whether something is low molecular SO2, we need to have a good molecular SO2 measurement. And I have some other thoughts on that if anyone has questions. And then finally, cans seem to be risky for our low pH wines, our cool climate wines, particularly come to mind, especially if we also have situations where we need to be using higher free SO2, particularly if we have challenging growing seasons. So beyond this, we might rethink how we actually approach SO2 addition, considering how slow the rate of oxygen ingress is in cans. So that general recommendation of 30 parts per million, or 30 milligrams per liter of free SO2, that we often think about at bottling, that recommendation has the expectation of using bottles and corks that have a faster oxygen ingress than cans. So that general recommendation wasn't designed for cans. And 30 milligrams per liter is honestly probably much more than you actually need for cans. And so we might consider adjusting that, lowering it to be something that is more appropriate for a packaging that has much slower oxygen ingress. There's always, of course, the caveat that it depends on the wine and the style you're trying to achieve, but we have to be flexible in order to take advantage of the benefits of this new type of packaging. So despite some challenges, I think that there's still a very strong case for using cans, and this is a very promising type of packaging. Lots of attractive benefits, but we have to be mindful of some of the challenges, since some canned wines have the chance of developing hydrogen sulfide if either copper additions or SO2 aren't managed properly. And so we hope to elucidate more on this topic as we continue our study and be able to relay that information to producers. So just a few quick acknowledgements. The Sachs Lab group, of which I'm a part, so my supervisor, Gavin Sachs, my colleague on this project, Austin Montgomery, and then the undergraduate researcher who's working with us, Ava Prime, as well as Dr. Luna Maslow of Beverages, who was a visiting professor in our lab from the University of Zagreb. And then, of course, all of our industry cooperators who are very supportive in our work. And then finally, funding from NSERC Canada, the Saltonstall Wine Endowment, and New York Wine and Grape Foundation for their support of this research. I'd like to thank you all for your time, and I hope you will ask questions about the work. Thank you.
Thank you very much, Rachel, for such a nice presentation and explain every detail of canned wines. We have a couple of questions. The first one is, please speak to the trend to move away from BPA in liners and the alternatives.
Okay. So BPA has been shown to be like a carcinogen, or no, an endocrine disruptor. So there are arguments that it is not safe, and there are different regulations. So I'm based in the US, and there are different regulations state to state as to whether you're allowed to use BPA in products and which products you're allowed to use it in. I'm based in New York State, and BPA is actually allowed. However, California, BPA is not allowed, and California dominates the US wine market. And if you are producing a product in a can, chances are you want access to that California wine market. And so while some smaller production, local products, smaller mobile canning lines may provide the BPA lined cans in New York State, if anyone is interested in this at scale, people are wanting to move towards the BPA, the non-BPA liners. And so what we're dealing with is what is called BPANI or BPA-NI, which is BPA non-intent liners. So it's saying that if there's any BPA, we didn't mean for it to be there in the design of that polymer. My understanding is that the BPA may not be as much of an issue as the legislation suggests it is, but that is what the legislation is. And so that is the direction that the polymer manufacturers are moving in. So there's producers, and then there's the people who make the cans themselves, and then there's the polymer manufacturers in the middle. And so these are three different businesses, three different parts of that product stream. And the people who make the polymer liners are moving away from using BPA. And the BPA liners actually work pretty well, but having to move away from it, they're encountering a lot more of these flavor chemistry inconsistencies for products. So the reason that a lot of this hasn't come up earlier was, one, because the BPA liners worked all right, and two, because the way that cans have typically been validated was in soft drinks and beers, and neither of those have any SO2, so this isn't an issue. And also a lot of the things that we test for is mechanical failure and not quality. So none of these wines are going to make you sick. None of these wines are dangerous. You know, the can isn't going to collapse or anything, but it's going to smell really bad and no one is going to buy that wine a second time. And so it's a different concern in wine than we have in other types of products. So just I guess in terms of the alternatives to BPA, it's just the BPA non-intent, and that can mean a lot of different things chemistry-wise. They're literally working on lots of different polymers. And I do think that the polymer chemistry is going to get to the point that it will be appropriate for wines. It's just not quite there and not quite validated because of the ways we've usually dealt with canned products. Wine is just wine and cider actually are just very specific products. They have SO2, they're acidic, and we want the flavor profile has to be a certain way. You know, we could increase the thickness of the liner and that would really slow down the rate at which SO2 could access the aluminum. But if we increase the thickness of the liner, suddenly we're going to scalp out aromas. And so we're going to decrease the intensity of the aromas. We're going to change the aroma profile. And we can't do that in wine because we don't have the option to just add more flavor compounds. If you do this with a soft drink, you can just add more soft drink flavor. That's fine. That's how you design a product. You can't do that with wine. So we're dealing with just a lot of boundary conditions that we haven't had, a unique combination of boundary conditions that we don't have with other types of products. It was a bit of a long answer, but hopefully I covered part of the question.
It was a very complete answer. Thank you very much, Rachel. Another question is, how much the total SO2 influence a wine can?
So total SO2 on its own as a metric doesn't really tell us enough about what the SO2 is doing, because SO2 can be we are only concerned about SO2 if it's chemically active and chemically labile. So that means we only care about SO2 if it is free enough to diffuse through the liner and if it's, you know, able to react with aluminum. If it's not going to react with anything, then it's not a big deal to us. So total SO2 doesn't tell us what the SO2 is doing. What tells us that is the pH of our wine. What tells us that is the alcohol content of our wine and the ionic strength of our wine. So all of those factors determine how that total SO2 is apportioned in the wine. Or also, I suppose, the anthocyanin levels. So what elements are there in the wine that are going to either bind up SO2? So if SO2 gets bound, it's not going to be chemically active. And then of the remaining SO2 that's not bound up, which part of it is most likely to access the aluminum? And we think it's that small fraction that can diffuse through the liner. Because if you have this liner, it should effectively be a barrier. The only thing is there is a mass transport of gas through plastic, and that is that small fraction of SO2. So just looking at total SO2 doesn't tell us how much of it is that molecular or the gas fraction. We need other chemical parameters. And I know that it's not common in wine to necessarily measure molecular SO2 directly. Like we look at total, we look at free. But what we're saying is that to deal with cans, we may have to also look at molecular. That might have to be a standard thing that we think about now when we want to when we have a wine that's destined for can. Like that's, you know, our marketing plan, that's our consumer segment. We want to make this canned wine. We can't just think about total. We have to think about molecular specifically. So you could have wine. I've made up model systems where I had, you know, very low free SO2, but proportionally very high molecular SO2. And then another one with very high free SO2, but proportionally very little molecular. Guess which one makes hydrogen sulfide? The one that has comparatively very little SO2, but it's the type of SO2. It's the chemical environment that SO2 exists in that makes it most destructive to the wine quality.
Thank you, Rachel. We have more than a couple of questions, just to let you know.
Okay.
Okay. Any work you can discuss with the use of tannin as an antioxidant, replacing in part the level of SO2 requiring for stability?
I can't speak to that personally from my work, but that is something we're actually looking at in some of our model systems. So, I mean, by working at it, I mean, like literally right now, I measured something earlier this week that did not go well, but I think it maybe is promising for what we're looking at going to the future. What we have found that we think is interesting, like related to polyphenols at least, we found that polyphenols could inactivate the aluminum surface. Or that is the hypothesis from the observations we had. So what we did is we took just plain uncoated aluminum and dropped it in wines. And if you put plain uncoated aluminum, there are lots of studies that show that there's studies dating back to like the 1950s, I think one from like mid-1930s, where people just like took aluminum shards and just dropped them in different types of wines to see what happened. And I mean, the results were just like a big table that just said check mark it stinks and check mark it doesn't stink. And, that's, just like uncoated aluminum. And we did this in some red wines and we found that we got no hydrogen sulfide, even though with a liner, we did get hydrogen sulfide, and that makes no sense. And it doesn't make sense if you think about, if we look at it the way we've always looked at it, but when you look at the polyphenols, polyphenols obviously can't diffuse through anything. It's a big molecule. But if we're dealing with uncoated aluminum, we think that there's some passivation of the aluminum surface. So we're thinking that these things like tannin might serve as like corrosion inhibitors, in addition to maybe having antioxidant activity. But it is too speculative really to say whether that could work. I think it's interesting to explore, and I think that there's probably some like work that's being done by different groups that probably could results that could be meshed together to kind of have like a new hypothesis on what's happening there. But it's a good question because we cannot say definitively what's happening at all.
Thank you very much. One more question is, could you please provide more details about sources adaptations and details of the hydrogen sulfide assaying equipment you used? And would you suggest winery labs adopt these new methods?
So, sorry, can you repeat that? This was the hydrogen sulfide method?
Yes, I can repeat. If you can provide more details about sources adaptations and details of the hydrogen sulfide assaying equipment you used, and would you suggest winery labs adopt these new methods?
Well, I will answer the second part first. So do I suggest that people adopt this? That very much depends on your winemaking program and like what information you want. If you've wondered about hydrogen sulfide production, if you have wanted to do accelerated or storage tests and know whether what you're smelling is hydrogen sulfide or something else, because that's also part of it. Sometimes people do identify an off smell and they think, is this hydrogen sulfide or is this something else? And so it may be of use if this is information that you want. That's very much an individual winery consideration. In terms of more details on that method, I can provide that hopefully in a couple of weeks because I have that manuscript open literally on my computer right now. I am submitting revisions with my supervisor right now. So we are publishing that method, all of the details, all of our calibration curves and validation and reproducibility, everything about how we work with that method, and how to adapt it using the glassware. We have a video demonstration as well of how it works, what the setup looks like. So that should be available in, hope the next couple of weeks. If you want information now, I mean, I am happy to share some like preliminary stuff we have, but it will be officially available shortly.
Perfect. I will say this very honest and out loud. We have more than a couple of questions and we don't have a lot of time, so I will be skipping some questions, okay? My apologies for that. So, Rachel, does the use of potassium sorbate in a higher residual sugar wine have any effect on the sensory of a canned wine?
This is the second time I've gotten this question. And I don't know yet. And I was actually talking to Gavin about this recently, about looking at the effects of potassium sorbate, because it's also used a lot, like obviously in other cool climate regions for like slightly higher sugar wines and stuff. I do not have an answer for that, but it's a question that other people are asking as well. So I'm sure that people will start looking at it.
Perfect, thank you. Do your studies focus on can liner and lid, or just the can, and have you noticed any difference between the two?
Sorry, between can, liner,
and lid.
Oh, okay. So we look at both, and we actually have another project going on where we're looking at the different effects we see to aluminum that is only in the headspace. So we make model systems where we take, say, just a glass vial, and we expose aluminum in just the headspace. So it would be like the can lid. And then we have ones where we have aluminum in the liquids, that would be like the can body. And then we have all of, say, our regular aluminum accelerated trials with aluminum coupons, where it's partially, where it's it's submerged, but like a little bit sticks out. So it's like more like a regular can, where you have some aluminum that has headspace, because even, canned beverages obviously have a little bit of headspace in the top. And we see different things happening. So there's a couple of things going on. The liner that's used on the can lids and the can body is usually the same. So in terms of the rate of transmission, we'd expect them to be similar. There's going to be points of different liner integrity at the point where it's seamed, because obviously there's force and like mechanical distortion that occurs when you have to make the seam. The aluminum alloy that's used for the body and that's used for the can is for the body and for the lid is also different. So the aluminum can body is 3000 series aluminum alloys, and the aluminum lid is 5000 series aluminum. And so that just means that the minor metal fractions or minor elemental fractions in the alloy are slightly different. So their properties are a little bit different. We standardize the can lids across all the different kinds of model systems, the systems that we're doing. So in our big storage experiment, we use the same kind of lid for every kind of can. We just use a standard one that is supposed to be the gold standard non-reactive, and we store our cans standing up. But we've also looked at different times people have stored their cans inverted or kept them constantly rolling, so that the wine is coating the different sides and the top at the same rate, because we have heard reports from different can producers that they see different kinds of corrosion, like visible corrosion in the headspace, than they do in the body of the can, or the part that is submerged. And so we think that there can be different chemistries going on, but it's not something that we necessarily decouple, because the whole effect is not like when someone drinks the can, gets a canned wine and drinks it, they're not tasting only from the lid or only from the body. They're dealing with the whole product. We don't think that it's like really worth decoupling at this point, but there's definitely different chemistry that can happen there.
Thank you, Rachel. Nestle, do I have time for one more questions, or you want me to? Okay, last one, Rachel, I promise you. So, in particular, have you observed any increased failure of liners at the site of joining between the lid and can?
We haven't visually observed that, but from talking to different the can producers, and also the people who produce the liners, they obviously work with real cans in their product design. They do say there can be some failures, some like micro fractures you get at the point where you have to compress the liner when you're making that seam. they don't notice it as a dominant. No one has commented on it as having a dominant effect, because we still see these problems in model systems where we don't have any, liner deformation because of, the crimping at the seam. We just have like a little aluminum rectangle that, we've cut out. We completely coat any part that could have been fractured because of, I guess, scissors even. We coat it with like a thick layer of non-reactive polymer. And so it's, even in systems like that, we still see this issue happening. So we don't think that if that is something, the, compression at the seam is an issue, it's not dominating the other issue, which is probably diffusion through the main part of the liner. Because just like on just from a mass transfer standpoint, there's a lot more of can body than there is of liner surface area. So just the driving force for that reaction to happen is going to be greater where there's more surface area.
Perfect. Thank you very much, Rachel. And thank you very much for all the questions.
Thank you very much for joining us. And as I mentioned, this was the last session of From Grapes to Wine Cool Climate webinars. We had 6 sessions. And if you attend any of these sessions, we would really like to get your feedback. And then we will be getting ready for the next season. And if you have any questions, please feel free to write to me or Francisco. And finally, I would like to invite all of you to the digital series of Minister of Agriculture. There are different sessions all online. And for more information, please visit Perennia's website. Thanks again.